We have just started learning about two-factor studies, and I'm going to go ahead and input the data that we're going to use in our running example. I described this example in the last video. We're going to look at the tooth growth, that is the cell length in cells in the teeth of guinea pigs, and we're going to see if that's affected by the dosage of vitamin C as well as the delivery of vitamin C, either with ascorbic acid or with orange juice. So I've already gone ahead and set up an R notebook here. I'm clearing the environment on line 12, loading the here library on line 13. That here library will be able to let me indicate any folder within my RStudio project, and I'm going to use the data folder to read in the tooth growth data that I've already put into CSV, comma separated value format. So let's go ahead and enter those in. Now, I want to go ahead and do something that I don't believe I've done in previous videos, and that is I'm going to look at the structure of these data. And I'm going to go ahead and put in a new code chunk here and use this new command, at least probably new to many of you, in which I use str for structure. And I'm putting in tooth growth so I can look at the structure of the tooth growth data. And what I find here when I look at the structure is that the length is numerical, NUM, and that's what it should be. This is our response variable, and this is the length in microns of these odontoblast cells. The supplement is actually a character. I want that to be a factor for my analysis because we use factors to indicate categorical variables. Notice that dose, as I discussed in the last video, is numeric because it is numeric, but we're going to turn it into unordered categories. So I want to go ahead and create these two new variables as factors, these two explanatory variables as factors. Now, the truth is that if we try to do analysis with our character variables here, that R is going to assume that we're wanting to treat those as factors. But I like to make everything explicit, and so I'm going to do that. So I'm going to go ahead and set this up for reading in as factors, and I'm going to pause the video for a moment so you don't have to watch me do all that typing, and then we'll take a look at what I've typed. Okay, so I've set up these commands. Before we actually run this, let's take a look at our data, and here's what it looks like. Notice that the supplement has these VC and OJ. The dose has these numbers. Now, I also want to show you over here in the environment that supplement is listed as a CHR, as we looked at before with the structure, and dose is numerical. What I'm going to do now is turn that character variable into a factor, and this is all I need to do in order to make that happen. Because if you look at it, again, it already looks like a factor. It's just that it's identifying it as characters, that is letters, as opposed to identifying it as this is an actual factor in our study. So even though it looks like a factor, it's not a factor. But by putting in this factor command, that will change it to a factor, and that's all it's going to do. Nothing else is going to change. On the other hand, with dose, these levels here of 0.5, 1.0, and 2.0 are numeric. We're going to turn those into a factor in which we have low, medium, and high. And by default, R does it as an unordered factor or a nominal variable. In order to make it an ordered factor or an ordinal variable, we'd have to add an extra argument, but we're not going to do that. So I'm going to go ahead and run this. And notice after I run this, when we look at our environment, that that supplement now is no longer character. It's a factor with 2 levels, although if you look at it, it looks just the same as it did before. But even though it looks the same, it's different now. It's a factor. And dose is a factor. It does not look the same. We no longer have numbers here. We have low, medium, and high for dose. Now that we've converted our data to factors, let's go ahead and get a summary. I'm going to go ahead and add a little code chunk in here. And I'm going to get a summary of all the variables. So I'm going to just put in tooth growth, and let's see what we get. Well, for length, we get a 5-number summary, the minimum, first quartile, median, third quartile, and maximum, with the mean thrown in for good measure. And notice what we get for the 2 factors. We get frequencies. We have 30 OJs, 30 VCs. For dose, we have 20 low, 20 medium, 20 high. So we have 60 guinea pigs all told, and each guinea pig is put in 1 supplement condition and 1 dose condition. Let's look at a little picture of this. So what we have are 2 levels of administration of vitamin C. And then we have 3 dosages, low, medium, and high, of vitamin C. And so we have some population of guinea pigs, and we've drawn out this sample. So this is our population. This is our sample. And from this sample, we've now assigned to each of these different cells that are a combination of our 2 factors. So we have a vitamin C low, a vitamin C medium, a vitamin C high, an orange juice low, an orange juice medium, and an orange juice high. Now in this particular sample, we have N equals 60. And so if we were to assign 60 into these 6 different cells, we end up with 10 in each cell. So how are they assigned? Well, in this particular study, they were assigned at random. So we take the first guinea pig, we randomly decide that that guinea pig, say, goes here in VC medium, the next one maybe goes in orange juice high, and so forth. So we keep assigning these guinea pigs until we end up with 10 of those guinea pigs in each of those cells. Okay, so this is called a completely randomized two-factor design. Notice that this is not a statistical analysis here. It is the design. But analyses often follow the design. So if you know the design, it helps you with your analysis, and it also helps you understand what you can say as a result of the analysis. So what does it mean to say completely randomized? It means that we randomized on both of those factors, that we randomized on vitamin C and orange juice, we randomized on low, medium, and high. Now, you could also have randomization on only one factor in some designs. Like, let's suppose that we were looking at different dosages of vitamin C, and we wanted to know how it differed for male guinea pigs and female guinea pigs. Well, in that case, we would not have a completely randomized design. We would only have randomized on one factor. And that's what we could say. We could say a two-factor design with randomization on one factor because we can't randomize the other factor. So let me go back to what we actually have, which is a completely randomized design. And because we have a completely randomized design, what is that going to say about our outcomes? If we find that there is an effect, we are going to have more of a reason to be able to state those effects as causal effects. Why? Because we've removed systematic bias both from the dosage and from the mode of getting the vitamin C in. That is the administration type, VC or orange juice. So when we find an effect that's due to dosage, or when we find an effect that's due to the way we supplement the vitamin C, provide that supplement, we are going to be able to say that we believe it to be a causal effect because we've removed systematic bias through complete randomization. In the other example where I said, suppose we were doing this for male and females, we wouldn't be able to talk about gender as a cause. We could talk about dosage as a cause because we randomize on that particular factor. So the design informs both our analysis and it informs what we can say as a result of the analysis. So this is the setup here. Let me go back to our notebook here. And here we got the summaries. And those summaries for factors are just frequencies. And for numerical variables are, as we're used to the term summary, those are the 5-number summaries. Another way that we could get the tables for the frequencies if we wanted to would be to actually use the table command. And this time in the past, you might remember using the table command for a single factor, but we can also use it like this for 2 factors. And there you see the 10, 10, 10 that corresponded to what I showed you here in this table. You can see it in the table here showing you frequencies. Now what we want to do, of course, is we want to, for each of those guinea pigs, get a number so that we have 10 numbers in orange juice low, 10 numbers in orange juice medium, 10 numbers in orange juice high, and so on. And what are those numbers? Those numbers will be the length after a certain period of time goes by of administration of vitamin C. I don't know if my data setup here, let me look to see if my data setup said anything about the time. It does not. It just says that there was we would have to go back and look at the original study in the Journal of Nutrition way back in 1947 to see how long this was done. But obviously this is done for a certain amount of time, and it's done for the same time for all 60 guinea pigs before we actually take our measurement. But then once we take our measurement, then we'll be able to look at those 60 values, 10 in each cell, and those numerical values, which are the length in microns of the odontoblast, will help us then make determinations as to whether there is anything to be said about the effect of supplement type and the effect of dosage. All right, now we need to look at the interaction first, since we're doing this in an exploratory fashion, and it doesn't make sense to talk about effects of dose and effect of supplement if they're interacting with each other. So in the next video, we'll look at the interaction and do some analyses to see if there's an interaction.